Morning, everybody. So, official start of this webinar today. You asked, a lot of people have been asking. We've done a lot of stuff on force and everything else, and we said finally we'll do something on torque. Torque is, we do torque here at Morehouse. We've learned a lot. We bought the machine from NPL, which is National Physical Laboratory in the UK. They gave us a lot of documentation. Some of that documentation is shared in the handouts part. So if you're not watching this on YouTube and watching it live, you can grab the actual handouts. If you're watching it on YouTube, you'll have to email us for some of those handouts if you want them. Most are covered in this presentation. So my name, for those that do not know me, I'm Henry Zumbrun, President, CEO of Morehouse. There's my contact information that is part of the handouts. If you have any questions after the fact, you can always go to our website and email them. If you're not connected via LinkedIn, for those that are watching or those that are watching after it's recorded, to connect on LinkedIn, message me on LinkedIn. That's my preferred contact method, just so we can connect. Then we see each other's posts. It's close to 10,000 connections, and it works rather well. And a lot of those ideas that we have these discussions then either become posts or become articles that we end up doing some research with our team and saying, hey, that's a really good question. We need to answer that just better than a 2-second or a 2-sentence answer. So anyway, connect on LinkedIn. Our purpose, for those that do not know, what makes us come to work each day is we create a safer world by helping companies improve their force and torque measurements. I said that our vision is great people, great leadership, great equipment, better measurements. So education is at the forefront, and educated customers, educated people are much better in this community for everybody. I know you all deal with customers, you deal with internal, external. If people know what they're talking about, a lot of times it's much better. So hopefully we'll get to that, and there'll be some good takeaways for you. So speaking of those takeaways, hope that you understand metrological traceability for torque and be able to have knowledgeable discussions about the types of torque standards and torque measurement errors. Really, the big overview of this is to get, okay, let's see what I need to have the traceable measurements, and let's look at all these errors that contribute to the primary standards, secondary standards that we're making measurements on the devices that are used to calibrate wrenches and whatnot. So just a little bit, torque is derived from SI base units. There's 3 SI base units, right? Length, mass, and time. And the interesting part over here is the kilogram, right, is now redefined, and it's redefined as terms of Planck's constant. It's an agreed upon set value, and that value is about 6.626 times 10 to the minus 34 kilograms per meter per second. Yeah, it's a lot to remember, but here's what we're looking at when we're looking at torque. We're looking at the meter, the length. If you're taking your CQE test for qualified calibration technician, these might be on there. They might ask them. I don't know if the kilogram is going to be on there or not. And then we have the second. And so 3 useful tools. You don't need to remember them. They're on there. But we're talking about the SI units of length, mass, and time. And torque is also called a moment, or moment of force, is the tendency of a force to rotate an object about an axis, fulcrum, or pivot. Just as force, think of our world of force as push or pull, compression, push, tension, pull. Torque can be thought of twist. When people come for a visit and we do tours, I always say, hey, our torque lab is the chubby checker lab because it's twist. Let's twist again. Lots of stupid songs to show my age that I like chubby checker and whatnot. There's the cartoon that people that know me know that this is a peeve to define units correctly. I do not always get it correct. I try to, though people go around saying foot pound, inch pound, and all these other words, right? And no one says meter Newton. So the correct definition of torque, just for me to share with everybody, is force times length. Foot pound is a unit of work or energy. It is a pound-foot is a unit of torque representing 1 pound of force acting at a perpendicular distance of 1 foot from a pivot point. So there's distinctions there. And if you look at NIST SI, the guide to the SI units, you're going to see that all torque units should be expressed in force times length. Types of torque standards. Now that we've set that what torque is, talk about some torque standards. One type for primary standard is a lever dead weight, and it consists of a set of calibrated masses that act on a calibrated lever arm or lever arm. Can be directly applied to the transducer in case of an unsupported calibration beam. Here is a picture at PTB. PTB is an NMI for Germany. They are probably making the best torque measurements in the world, meaning the most precise torque measurements. Best is a vague word, but if you want something calibrated to the absolute lowest possible uncertainty when they're using the reference standard, PTB is the lab in all of the world that can do it. The lever arm will be connected to a bearing, ideally, that's in here, to eliminate bending from weights and masses and to minimize friction. A lot of you out there, I'm sure, do not have just put weights and arms on it. Some manufacturers will say use this arm up to 100 pounds inch, or they'll say inch pounds if they say it wrong, because everybody in this country seems to say it wrong. And then you just hang that on a cell, and we'll talk about what that does. And this type of system is used for static torque calibration. There's some standards they need updated. BS 7882, the DIN standards, ASTM E2428 is the one in this country that most people use. Typical systems, this is a very large lever arm, and typical systems tend to be chain loaded. And all that means is you pick up one weight and then you have to pick up the next weight in line. Some of these systems, people that are out there, and I feel bad for you, are just throwing weight. You just have to manually lift weights onto a pan. And sometimes it takes a lot of time to lift 50 pound force weights, 25 pound force weights on the arm, or even higher. I know some labs have higher weights. Many do not, though. It takes a long time on and off, and there's a lot of additional errors that we will talk about later from stacking those weights. There's also pneumatic systems, where you have air-controlled systems, and there's automated systems. So, lever dead weights are used in two different types of torque arms: single-ended, dual-ended, or radius-ended. Torque is generated by the application of a known force at a known radius from the center of rotation of the torque transducer. And then radius-ended beams are typically designed with a ±8-degree usable arc within which the calibration accuracy is unaffected. Single-ended beams do not have a constant overturning moment, as the dual radius arm would have, and may have additional error as compared with radius-ended beams. So in the tests that I've done, there are many manufacturers out there, and what I've showed are usually dual radius beams that were shown, pretty equal on each side. You can do some testing and other stuff with them. Single-ended beams, when we went down to Washington a while ago and used to present classes live, we would do some tests with single-ended beams and everything else. They do not work nearly as well as radius-ended beams because they change, right? You put a lot of weight on it and it changes. Somebody might have a better design out there. I have yet to see it. If I'm going to purchase a single-ended beam, my options are single-ended beam or dual beam, equal sides for clockwise, counterclockwise of length from the center point. I would choose a dual-ended beam with the 8-degree usable arc. Yeah, just because the single-ended are much less accurate and carry higher uncertainty. Then we have some pretty cool stuff. This is PTB. Again, this is electronic transfer reference as for DKD-R-3. PTB uncertainty of this system is around 0.02%. Now, what's interesting here with PTB, this is a transfer standard. And so what you're looking at, that looks like a torque wrench on top. That is a transfer standard that's hooked up, and it's made by HBM, I'm told, and they can achieve 0.02. When PTB puts something in their lever dead weight system, they're achieving 0.002% or better, so about 10 times better when they're using actual weights. This we're progressing into simpler cal. Really great uncertainty though. 0.02% for a transfer is just phenomenal, and that's why it's shown. The other thing, the why I show it is because if you do happen to use PTP, you're going to want to specify what you want. If you send it in there, you're going to have to specify if you have something that's bolted, if you want the bolts loose or tight, and you're going to have to specify that you actually want this with dead weight. Okay, so I got something that said we can't hear. Hopefully that's only one person and not everybody else. Check here. So can everybody hear now? Looks like, yeah, okay, thank you. Thank you all. When I see that question comes in, I usually get worried. So anyway, the other type of torque transducers, these are some of the ones that we're working on here, is a reference torque transducer, where you have a reference torque transducer and you compare it with an unknown, you bolt them up, you typically have bearings, other plates, other adjustments. Torque can be applied using a motor or hydraulics with the torque controlled by means of calibrated reference torque transducer and a feedback loop. We have automation for our force machines. This is similar, monitoring that feedback loop of the reference, and then hopefully transferring that to the unit that you're calibrating, the DUT, device under test, or unit under test, UUT. And then other similar designs may take traceability from calibrated load cells, measuring the reaction force at the end of a lever arm. So typically what happens here is you go to PTB or somebody else that can do larger torque with arms and weights. Hopefully they have a bearing in place to eliminate the friction, dual-ended arm. They calibrate your transducer, your torque transducer, then you use that as a standard, as your reference to calibrate other transducers. You can achieve pretty good uncertainty doing this, and it can be automated and quick. It's still a pain to bolt everything up, of course. And these can be used to measure static torque, yet has an advantage of being suitable for continuous torque calibration, whereby the applied torque is applied over a much shorter time. So disadvantage is the uncertainty of the applied torque will be much higher because, hey, we have to account for metrological traceability. We have to absorb the uncertainty of the reference. Now we're absorbing that. We're doing repeatability, reproducibility, all kinds of studies, everything else. So much like, dead weight and arms are going to be a magnitude better, usually 10, 50 times better than this type of system. Some measurement errors, getting to the point of what we're all here to learn about today after some of the overview, is using some things that we see labs do, is using mass weights instead of force weights. And I hate that I still say this, because it's not that terminology for those that are out there. It's really using weights that weren't adjusted for local gravity, air density, and air buoyancy. It's a lot easier for me to say this is your error. It's using mass and not adjusting it for force is the correct terminology. Or correcting it for force. Calibrated beam, deflection and temperature, misalignment, load position, worn drives on the beam or transducer, introduction of bending or parasitic effects, bending forces on an unsupported beam. These are unavoidable, and temperature changes. So if we go for the first one, if anybody knows Phil Stein, Measure for Measure column, Phil Stein, he's also wrote some of the CCT primers and other texts. Very knowledgeable person, great contributor to the field of metrology. He wrote a paper that's called The Gravity of the Situation, and this is a summation of that, which said it's very important that the gravitational value for the laboratory is established. The effect of not doing this could be a variation in the force produced by the weight of perhaps 0.1% or more of reading. Now, from the pole to the equator, there's about a 0.5% difference. This 0.1% is coming, I think when Phil wrote this, and Mr. Stein wrote this, coming from like looking at some of North America. North America does have more variation than 0.1%. So it's a really good number. Though when I speak about this, I want to tell you that maximum, if we look at it, could be as much as 0.5%. And it's strongly recommended that you establish the local value of your gravity-free laboratory and use weights that have been calibrated at that gravitational constant. Look, that's what Philip Stein, there's other ways to do this. You can have, instead of using NOAA, which I'll talk about, you can have gravity measured at your site. We had gravity measured twice at our site, and in 20 years, the difference was 0.1 part per million. It might be a little bit of overkill if you're in North America and can use NOAA. Like I said, I'll show that. And the expanded uncertainty from this calculation is likely to be with, if you do use NOAA, it's likely to be within 5 parts per million anywhere in the US. This uncertainty as a maximum or actual reported belongs in an uncertainty budget for pressure, torque, force, and then you have to report other values. So there's different things. Like I said, we hired a firm to do this, and that firm got us within super, super low numbers. So looking at that, weights used for torque and force standards, there's a must in there, and it should be a must, or it should be a shall or must. They shall be corrected. If you want to make the right measurement, they shall be corrected for local gravity, which I said from the equator to the pole is a 0.5%, and then it's about 0.2% across the US. Material density, and that's in extreme cases, material density, and then air buoyancy when used in air, correction is approximately 0.12%. That can change. In our lab, it's 0.117%. So there's a lot of different things that go into this. And then buoyancy is that Archimedes principle, where air pressure under the weights cause an upward force which reduces the effective forces generated by the weights, and therefore the mass must be increased to allow for this. If you do use just the 0.012%, you're much better than doing that correction, more than likely than doing nothing at all. So I would get your density measured. So we have lots of blogs on this. You can go to our website and I just wanted to give somebody an example of how to do it. Obtain the measured force value, because we are talking about force times length. So, hey, I want to generate 10,000 pounds pound-foot. Fine. I would use 2,000 pounds on maybe a 5-foot arm. Anyway, the way this works is 10,000 pounds. You can go to GeoPlanner, which gives you the longitude and latitude. Then you can go to NOAA, predict your gravity. Like I said, it's usually within about 5 parts per million. And for here, we just used Denver because Denver's up high, and there were a lot of shows, and a lot of NCSLI was in Denver, A2LA was in Denver, and we're up pretty darn high. Denver to Florida would probably be pretty extreme, you know. In any case, looking at the estimated, you can estimate where Denver is, and you can use the formula force times standard gravity, local gravity, 1 minus d over d. And if you look at this, it basically says, hey, if I want to generate 10,000 pounds of force in Denver using these weights, using a stainless steel weight with that approximate density, I'm going to need to have my masses, when I weigh them, should weigh 10,011.89 pounds. And that pound should be LB. It should never be LBS. I need to fix my slide. Little things you see each time. Weight handling. So hopefully that made it clear. You can go to MH Force. Like I said, we have a guidance document on correcting for force out there. We have Excel sheets on our website that you can just, it makes this easy. You go to NOAA, plug it in. It can convert mass, your mass values to force. So do you need to get your weights adjusted? Probably not. If you like, you can use your current weights if they're mass and just use the gravity correction and everything else and just say, okay, so 1,000 is really 1,000 and 1.1 doesn't matter. You just your nominal values that you generate for your customers might look a little weird to say we generated 1,001 pound-feet instead of 1,000. Not a big deal at all. So weight handling, the people with AKO and some other arms, the physical lifting of weights onto and off a platform creates additional error. Of course, if you've ever done it, you have to see it. The weights spinning around in air, you're not going to get them perfectly centered and other things. No one is like calm and collective when they're picking up 50 pounds of weight where there's not some vibration and there's not some drop, a little bit of drop on the system. To minimize that error, it's decision time, right? You can automate. We have automated solutions with for some arms where you can put a load cell at the end of it. Then it's not going to be, the uncertainty is probably going to be larger than the weights, depending if you corrected for gravity and everything or not. But if you have weights that are corrected for your local gravity, know the air density and the buoyancy, there's not much else to do without sacrificing a lot of uncertainty than just living with handling the weights on and off. So it's a decision that needs to be made, but know that there's error to that decision. So that being said, the other things we have is calibrated beam deflection and temperature. The material the beam is made of will determine the amount of weight that can be supported by the beam. Using more weight than the beam is designed for may cause significant deflection. The properties of the material of the beam will expand and contract, changing the length of the beam. That's temperature dependent. That's also depending on the material with what you're doing, what you're putting on it. Temperature effect can be minimized by maintaining the room temperature of the calibration laboratory at the same temperature. So I went down to NIST for a session on torque, and this one person was talking. I thought they were the most brilliant speech. He gave a fantastic speech, talked about uncertainty of torque, talked about errors, everything else, and then immediately everything was discredited from that whole discussion when somebody nudged me and said, "Hey, this guy's talking a lot. I've been to his lab. He only maintains his temperature within plus or minus 5 degrees." And that can be a huge, huge error source on the material. And I was also told that he doesn't correct for any of that too. So whether it's right or wrong, you talk about things and you talk about discrediting people, that length will change with temperature. You can use arms made of carbon fiber that will have less change, but back then, 15 years ago, we weren't seeing many carbon fiber arms and the other stuff. We were seeing steel. And we weren't seeing a lot of the aircraft grade steel that we see today in some of the really, really nice arms. So misalignment, another error, very difficult to perfectly align any transducer. Always going to be misaligned, right? Always. It's just you're going to try to get the best that you can do. There's different types of alignment. There's parallel offset, angular offset, combination when you have both. And there's going to usually be some mismatch of the two axes that will give radial, angular, or axial misalignment. And one way to minimize it, and I don't have a picture here, you can dig through the NPL stuff. I'm happy to share it, is flexible coupling elements. And that's what we have on our machine. It's very expensive to sometimes to put these elements on, and they come with their own inherent flaws, like the ETP, some types of adapters and how you made them and how you design them. I don't want to discourage anybody from it. I just want to say that it depends what you're chasing and how good your measurements are. And I'll get to this later. The way you can prove this out is do a good ILC. Get a good known cell, send it to us, Morehouse, send it to PTB, send it to an NMI, send it to somebody that can give you a very good reference value that you can trust. Bring it back and test your machine. If you have a lot of this misalignment and stuff, it's probably going to show up depending on the cell and how much the cell can compensate for this. Worn drives. I go into lots of labs and I see this all the time. You'll go look over at something and you'll see a square is not a square. It's worn. And then you say, well, why don't you get a new one or get that fixed? And they've just been using it that way for ages. If the fittings are worn, the proper torque's not going to be generated. And it's not uncommon for the error to exceed 10% of the desired torque value. If it's really worn, you could be off, and no one's going to know, right? 10% is a huge number. An ILC test will show this all day long, or should show it all day long. Introduction of bending and parasitic effects. Influence of bending and parasitic effects on the transducer depends on the transducer's design. Reproducibility of the device when calibrated in different orientations can be an indicator of bending or a bad design cell. But typically, if it's going to bend, you're going to rotate the cell, and if you're going to have like various problems with bending, it should show up on with some reproducibility test. This paper is attached for those that are listening live here and on the GoToMeeting. You can download the paper on bending forces on supported beam. So be aware of the influence that bending can have on a measurement result and quantify it if possible. Transducer should be held rigidly on the mounting plate. The fit of square should be as good as possible to minimize any slack. Here we have an unsupported beam, right? And what NPL did in this paper is they took 3 beams, A, B, and C beams, and they calibrated different transducers with each of those beams. So we ended up getting a transducer A, which is 2 kilonewton meter transducer, transducer B, 200 newton meter, and transducer C, a 1 kilonewton meter with a 1 kilonewton unsupported beam, a half kilonewton unsupported beam, a 1.5 kilonewton unsupported beam. So they did all of this, and then they looked at the deviation of these errors with these beams, and no surprise, looking at these graphs, see the 1 kilonewton transducer with a 1 kilonewton unsupported beam, look at the errors, the deviation of 0.08%. If we look at B, the 200 newton meter with a 0.5 meter unsupported beam, that was also like at the lower percentage of torque values. The overhung moment was generally pretty large with that. So looking at that in a bit more detail, transducer B was then calibrated with the 1.5 kilonewton arm. So the first one, we just saw some deviations between the points. And then the 500 newton meter beam weighs 16.6 kilograms. So looking at this one, there's quite that deviation went from 0.08 the whole way up here to what? Well over 0.1%. And this is all in the paper. So basically what this is saying is the weight of the unsupported calibration beam in relation to the capacity of the torsion cell has a significant effect on the transducer output. Worst region typically affected is 0 to 20%, where the weight of the beam is most significant depending on the design of that torsion cell. And under certain conditions, an unsupported beam achieved results within 0.02% of the reference value from the 20 to 100% range. So what they did is they calibrated all these cells in the NPL machine that we have now, calibrated them with beams, reported the deviation of them, and then that's where we saw that 0.08%, depending on the various ones. Looked at how close they started to agree at specific applied torque points, and then they varied the different beams around and showed that it was very significant at 20% or less. And you can kind of see by this chart of that they have with the 3 cells and everything else, that deviation versus the unsupported beam is still yielding pretty high, which is interesting when your calibration provider might use an unsupported beam and you see their uncertainties well below these 0.08s, well below these 0.02s. You kind of have to start questioning it if they're using an unsupported beam. If we start supporting the beam with something like bearings, we can eliminate the bending effects due to the weight of the lever beam and weights. And depending on its quality, the bearing itself may introduce errors such as friction, and performance of bearing still requires evaluation. We're working on bearings here. They are expensive when you start setting this system up. And then you run into the question of, does it replicate use? Maybe. right? Typically, these cells are mounted vertically, the ones I see. There are some that are transfer standards, right? But typically, they're going to go in a wrench calibration system where they're going to put them vertical, they're going to calibrate them horizontal and then use them vertically. So does that replicate use? Probably not. So here we just have, we're working on carbon fiber arms. We've been working on them since 2021. This project goes and then it stalls. The goal is to have one arm that replaces maybe three using carbon fiber, so the temperature coefficient for expansion, and using a different drive. Instead of square or hexagonal drive and stuff will take longer to wear. There's a lot of stuff going on with arms and everything else, and scalability. Like it's very difficult to scale up. So, and you're going to have some metal at the end. Anyway, that's just something. There's a question mark there whether we'll ever release them or not, but it is something we're working on, always trying to make better things. So this is going to be a little bit of a discussion. These came from Stallville. Excellent manufacturer, excellent system. Stallville makes great cells. I've had the privilege to test a lot of these, a lot of their cells up to 2 kilonewton meters, and they work really well. If you have the kit, we can calibrate the kit on reference, or we have all the adapters to calibrate them. Though these slides came directly, had the privilege to present with some people from Stallville, and they were showing a lot about, David Wan was showing a lot about cross variable forces, which is referred to cross force. It's a force that acts on the measurement system or transducer in direction that is not aligned with the primary axis or intended direction of the force being measured. This type of force introduces unwanted influence into the measurement system, which can lead to errors or inaccuracies in the recorded data. So what I was talking about earlier, if the transducer is designed to measure force in a vertical direction along the primary axis, a cross force would be any force acting in a horizontal direction or any direction that isn't aligned with the vertical axis. These forces can cause bending, twisting, and other distortions in the transducer, affecting the accuracy of the measurement. So if you want to make better measurements, minimizing or compensation for this cross force is critical, right? And here's some scale points, and here's what they're showing: vertical alignment and then horizontal alignment. They happen to do different tests on the Solwa, and you can see it's quite a different value. And the summation of this is there's better cells available for the measurements. And one of those, if you're concerned with cross-force variables, one of those better designs is a web-style transducer, which greatly reduces sensitivities due to bending or side loading. We have some of these. They're not on the website. We do sell torsion cells, and we do make some of them. So if you have interest in cells, we can do that. Next year we'll hopefully have more on the website and whatnot. Or these are the Stallville systems. By Stallville setup if you want. Really good stuff. I could recommend it. There's also a lot of other good manufacturers in there. Don't think I'm biased just for Stallville. I just had the pleasure of presenting with them, and I know how their cells are made. The measurement is made much closer, reduced lever to the point where the reference and object are mated. And then with their cells, they have overloads of up to 3% are possible without mechanical damage. They also have chips in their cell that will tell you how much torque the cell has seen. So one of your techs overloads it, it's going to say if you had a 100 Newton meter cell and the tech took it to 400, it's probably going to show you, oh, here 100, 250, 330, and then no more reading anymore. And it can date and timestamp that too. That basically says, hey, on October 15th, 2024, this cell last read well 350 Newton meters on a 100 Newton meter cell at 11:30. And you're like, wow. So right after 11:30, the cell was toast. Somebody overloaded it, and we could see it going in that direction. The other thing about cross variable forces is from as low as 10% of nominal, a web cell becomes desensitized to bending and side loading. And that's, this is a draft of the paper that they were working on. So just interesting points here. overall. Temperature effect. Many of these torque systems, same with force, are four-wire systems. Somehow a manufacturer made a four-wire system, which is fine. That just means they do not sense that difference in resistance. And when I say it, when a cable is not wired for sense 6-wire, then switching signal cables will produce additional error. I have all this in the force book, everything else. These errors can be quite large. Depending on the gauge of the cable, there's also temperature influence and everything else. 4-wire cables will introduce additional error based on the thermal coefficient of the material used and the use of gauge wire. Like if you're using 12 gauge wire, it's going to be much different than if you're using 26 gauge wire, right? 12 gauge is really thick and heavy. It's going to drop a lot less than say a 26 gauge wire. And I believe like a 28 gauge wire, it's like 0.1% per foot. I don't, I'm trying to remember that. I don't know. We have to look that up. So if you have to replace your system at any time and you're buying something new, the thing I would always make sure you can go with a 6-wire sensing system because you can just eliminate this additional error right off the bat. And if the load cell only has 4 output wires or torsion cell, you can wire almost any cell to a 6-wire system. You just jump positive sense to positive excitation and negative sense to negative excitation. Then the meter will work. No secret there. 4-wire load cell or torsion cell that's wired A, B, C, D. 4 wires you can wire for sense. Cosine error. One of my favorite discussions. We have a blog on our website on this. So a vector is a quantity that is defined by its size and direction. Every time the effect of a known force is evaluating on a static or dynamic system, all applied and resulting forces should be determined by both their magnitude and direction. If one says that a 100-pound force is applied at point X on a table, without fully defining the applied force direction, then an infinite number of solutions, each with its own set of results, can be generated. Cool stuff. So what does that mean? And you can evaluate this, right? The effect can be evaluated. Different methods might be used for various coordinates. This is Cartesian, polar, cylindrical, and spherical. We get into really nerdy stuff with this, but in most simplistic form, the applied force vector can be expressed in a 2-dimensional flat plane, x and y directions, right? Fx, Fy. There we have our system. Let's look at a real world example. This is an advertisement from a company. So they said before there wasn't any way we could know the torque applied. And if we just look at this example here and how we would apply cosine error, we have a force of, let's just say 150 pounds and a length of 2 feet. Since torque is force times length, we have 150 times 2, 300 pound-feet. Is it correct? All right, so above calculation that I'm showing everybody can be true if we're at 90 degrees. And that simply means that if this picture were changed and I had, remember back in geometry class, and I had a 90-degree angle here, that this would hold true. You might say, hey, how we measure the length, how well do we know this? We get into this. This is clearly, from this advertisement, this is clearly not a good example of how you measure torque with this large error. So if we use simple x and y planes, and let's assume this A right here is 40 degrees. Someone might say it's their calibrated eyeball, might say it's 30 degrees. Someone might say it's 35. You can plug this in for whatever you think it is, the formula I'm going to show you. But let's say it's 40. Only a portion of the 150-pound force generates torsion at the center of the pipe, and the rest of it is spent on pushing the pipe upward parallel to the wrench direction. So what does that do now? So say A is 40. Like I said, if you think it's 35, you can use this formula, throw it in. So it basically says the torque generating force will be 96.42. And then the force applied parallel to the wrench handle, cosine A, cosine 4. This equals, so 150 times cosine of 40 degrees equals 114.91. Then the generated torque at the center of the pipe, actual force, right, 96.42. 96.42, we multiply that by 2, and we get 192.84. What does anybody think about that? You're saying, oh, hey, this is a great way to measure torque. You put it in your marketing bulletin, you put it in everything else. And if people out there are doing that, that error is huge, right? Actual error based on rough calculation is 36%. And that error, like I said, goes all but away is if we establish this at 90 degrees. We create that right angle. Would have been super easy to retake this picture, right? If they would have taken this picture and just moved this up to 90 degrees and made their advertisement, I wouldn't be able to come over here and pick on it for this webinar today. Traceability and torque, important topic. What do we need to have in place to help ensure we are making traceable and meaningful measurements? Well, this is what I like to call the measurement traceability chain. I wish I developed this. This was developed by a good friend of mine and used at NIST and some other places to teach traceability. And we have these 7 elements, and they're all held together by this one here, measurement assurance, which we'll talk about, and it's appropriately placed in the middle of the chain. So, measurement traceability, definition, a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. What's that mean? So that means we're gonna go to some lab to calibrate, send our devices to be calibrated. Hopefully their scope of accreditation is correct. And they put on their SOAP, their CMC, their calibration and measurement capability. This one's from Morehouse. The comment at the bottom, silly, but we can generate torque known from 1 to 200, 2,000 newton meters or 2 kilonewton meters, about 0.003%, right? That the equivalent is about 1475 foot LBF. And we can do BS 782, E2428, regular single runs with accuracy statements. We can do all that. If we calibrate your device, what you will absorb from us is 0.003% plus significant contributions from your device. You will never be able to make a measurement better than 0.003%, right? You have to absorb that reference. If you go to another lab that has a 0.5% CMC, you cannot be better than that 0.5%. And this is generally how this works, is traceability through a National Metrology Institute. You typically have SI. We're in the US, so I still put NIST in this. So torque measurement, 1 standard deviation. NIST does not do torque. So let's say we start at PTB. PTB, 10 parts per million, 0.001%. We bought our standard from NPL, was registered with the CIPM. That's a big deal. Did all types of intercomparisons, everything else. We even sent cell to PTB, which I'll show you later, some of that, and check the system. And we are realizing our uncertainty about 0.015. What I typically see with accredited calibration suppliers are numbers, believable numbers between 0.02 and 0.5%. Some might be lower. Some might claim lower, like a 0.036 or something like that, and they may not be able to do that. They may be doing calculations with mass weights instead of force weights, which we know automatically is probably going to bump them quite a bit, maybe even 0.1% when they're claiming 0.03. And then we get to working standards, typically a 0.5 to 1%. And then field measurements are torque wrenches. I know people out there, these are just rough numbers. Look, we know torque wrenches are out there that can do 1%. We know torque wrenches can do 4. We know multipliers. There's so much stuff in industry. The whole point of this is just to say every step in this chain, every step in this pyramid, if somebody sends something to us, Morehouse, you're not going to get better than this. You're going to absorb this number. If you go to a accredited calibration supplier, you're going to absorb whatever number they have for measurement uncertainty. And that'll help you establish your metrological traceability, and all measurements are subject to it. Uncertainty, often defined as doubt. The BIM, a non-negative parameter characterizing dispersion, blah, blah, blah. I like to think of it as just simple. Look, how close a particular test result, the product of one laboratory, is to a reference value with its own associated measurement uncertainty. My good buddy Greg Senker, which I throw his name out here, hates people often say, use the word true value. We never know the true value. So here's the dig. If you start seeing true value, which I'm sure I have it in some of the old ratings I did 10 years ago and whatnot and haven't corrected it yet, we never know the true value. NIST has some awesome videos online and they talk about the cost of knowing the next decimal place and how large that cost is. We might know something to 5 decimal places, but there's still doubt there. So you never really know that true value. There's always some error in the measurement. So if I can convey anything to anybody besides all the good stuff is if you see the word true value, stop using it. Don't use it in your vocabulary because we do not know it. Unless you're talking about Rick and Morty, pure flatness. And if you want, look that YouTube video up on Rick and Morty, true flatness. It's quite comical. So, and then the further away from that, the primary standards, the larger the uncertainty becomes. That's just how we go with, your reference. The further away you are. I bought a torque wrench off of uh, Amazon one time because it came with a cert and it said, this calibration is traceable to NIST. Like NIST doesn't do torque. Calibrations aren't traceable to NIST. They're traceable to the SI typically through an NMI, such as like PTB or whatnot. Though I don't know how far away this thing was, right? It could be 10 levels down that they're doing some measurement. So anyway, that's just know further away you are. Other things we want to consider, of course, are documented procedures for our calibration. Use the appropriate methods within the scope. Measurement assurance. This is SPC. These are control charts. Man, I love this stuff a lot, and control charts confuse me. Those that are out there that have done control charts, I know some people do them with ease, and other people. ASTM has some good guidance about 3 standard deviations. And when I say they confuse me, it's how many measurements do you need? What do you want to accomplish? And there's a whole lot of information on getting the right standards and tracking this. I'm a huge fan of SPC. I just never, one of the things that I always struggle with is including how good is what I'm testing, right? We know our standard. We do intercomparisons with with other people. We participate in ILCs. We send cells to PTB, get them back, do those comparisons. Though they all check out, but if I run a standard every day, I'm going to have this variation, and what variation is acceptable. How many runs do I need to take? How many data points do I need to take? There's a lot there when you start going into control charts, and they're not that, like I said, they're not overall. They are not super daunting or challenging. You do 3 standard deviations, you do other stuff. It's just once you start trying to find that perfect standard, that standard that 3 months from now it's going to read the exact same thing. With torsion cells, it gets difficult, and then you have to figure out drift and some other stuff in there. So anyway, enough of everything that's going on and how to monitor this. I'm hoping to, Dilip, Greg, and I are hoping to write a guidance document on it. So those practices, statistical process controls put in place, technical competence, the ability of the person to do their job comparatively and on the same level as other professionals in the field. And then this is the old 17025, shall have competence of all who operate specific equipment. I like the language in that, so it's in there. Demonstrating that technical competence. This is where people do weird things, like I'll give my best tech to do it. Well, you should get all your techs to do it, right? And proficiency testing determines the performance of an individual for specific tests. And here's, Z-score indicates how many standard deviations an element is from the mean. So I believe this test was one that we did with PTB involved with it, and the reported uncertainties in Z-scores. EN ratios, as you see on the right there, it's the lab reference. This is the further away you get from 1, meaning under 1, values under 1 are good. So these numbers having 0.10, the highest value, it means we're 10 times in. Usually if you get close to like a 0.75 or something, you start to worry, tweak your system. These are fantastic numbers that we got on this report. And here they are blown up, clockwise and counterclockwise numbers, and z-score, the standard deviations away from the mean, all low, great values in this PT. This is what you want to see. Really, if your ENs are anywhere under 0.75, you're good. And when someone will say, well, what if it's higher than 0.7? Oh, it's just evaluate it, right? Maybe you raise your uncertainty a little bit. Yeah, great numbers. You want to see them under 1. And then the realization of units, define the units correctly, right? Do your corrections. If you're using mass, a conventional mass, convert it correctly to make your torque measurement or force measurement. Periodic recalibration, one of the things that helps keep us all in business, right? Calibration intervals are probably established for maintaining. Hey, you know this. And same with adjustment criteria. You know this. Like I always harp on people, when do you adjust something? Some people say, well, always tweak it to nominal. Well, if something is 3 Newton meters heavy today, and I said heavy today, and then I tweak it to nominal, and next year it is 3 Newton meters light, guess what? If I wouldn't have tweaked it, it would have been pretty much at nominal. So it's adjusting all the time is a good way to get yourself in out of tolerance conditions. So you should establish your own run rules. What is my adjustment criteria different from manufacturer specification? Manufacturer says 0.1. Maybe I want to adjust at 0.07, 70% of that spec. If it's 50% of the spec, maybe I don't want to adjust it. I want to see what it does next year. The whole point is you should establish enough history and baseline, and so you start knowing when your standard's drifting, and you should also start knowing how frequently you have to have it calibrated. The cool thing is if you start getting history, you can throw it in Chat GPT, you can throw it in AI. AI will do some cool stuff and give you some predictive analysis, bootstrapping, confidence intervals. AI is really getting cool as I say this, and there's other things. We do have a blog on metrology AI. If you go to our website, mhforce.com, you can check it out. It's just, I would just posted some examples from this certificate, 3 years of NIST cows and doing some predictive analysis. Look, it's just more tools in your tool belt. Our machine, really cool machine, 2 million euros to build. We didn't pay that much. We bought it from NPL. This one was not going to come up for sale again. It is a very slow machine to use overall, though we have a realized uncertainty of about 18.6 part per million, which translates into a calibration measurement capability of 0.003. Vertical design, so if we put something in there, you're using a wrench calibrated, typically it's going to mimic, when we talked about those cross variable forces, it's going to mimic if vertical, twin beam carbon fiber lever arms. I think it's like 0.3 times 10 to the minus 6 per degree C expansion rate, super low. Alignment of the tapes is like 5 parts per million. The masses themselves, 7 parts per million, the worst case, adjusted for local gravity and air density and everything. So on completion, it shipped to Morehouse. We had the English NMI NPL scientists with us for about 5 weeks, teaching us all things torque back in 2010. Each where we went out torque all day and drinking all night. So hopefully made our friends from across the pond proud, hanging out with them and having fun. And the things that we can do are add for ourselves. So, we can help you satisfy the SPC, provide you with a good instrument, a good system to monitor. That system can be used to do ILC. You can do a direct ILC with us up to 2 kilonewton meters. It can be used as a tool to help figure out your system. Do I have these bending? Do I have these errors? Do I have all this misalignment? and you can start from there. It's a pretty easy check to help quantify setup and system errors. So I hope that everybody got something, at least a little takeaway from this pretty high view. Like we didn't really dive too much into the weeds of everything, maybe a little bit on cosine error and how to do that. But hopefully you have the tools now. You can go to the website, you can dig deeper into the blogs, into the books. If you are interested, it's in the link. There is calibration training. This is 3 days a week. I'm very happy with it. It's 40 weeks total now. We upped it. It might be even longer if you do sign up for it. And it's 3 emails. They're all educational. There's a few that are about us. There's some that are on company culture. There's 20 plus that are on torque. 80 plus that are on force. There's some combinations on gauging things and what strain gauges do, what resistance measurements do. High resistance, low resistance. Lots of different stuff that's in there. Decision rules guidance is in there if you're struggling with decision rules. We also have decision rule guidance document. All this stuff is free. Look, trained people are, or they say trained customers are better customers, but we're all customers of one another, internal or external at some point. If we can make better measurements, if we can help anybody do that, or you get some takeaways today that you can improve your system, guess what? We're all better off. You come into work each day, you're making measurements, you're doing everything you're going to do. As soon as you get better, everything you measure gets better. It's the change is just phenomenal, phenomenal. And that's what I have to say. So if you're interested in learning, take advantage of it. Like I said, it's free. We want to share everything we possibly can. That's our time on Earth is maybe limited. You think so? Why not do something with it? And I'm happy to share and help anyone with the knowledge I know. I don't know everything, so I'm sure there's things in here that can be corrected, and we just keep correcting them and getting better and getting better together with all our combined knowledge. So thank you all. Other things we have here, YouTube channel, if you want to see some videos, if you're a visual learner, great. LinkedIn, as I said, if you connect with me, Henry Zumbrun, on LinkedIn, message me on LinkedIn, preferred communication method because I have it on my phone. I see it all the time. The email inbox, sometimes things don't get through. We have large spam filters because everybody wants to sell you everything in the world, right? So that being said, LinkedIn just seems good for me. We also have CMC calibration measurement capability calculators, all types of stuff online. If we go to it again, the training's super simple. Sign up for this. We say it's the mastery series, so we'll respond to that. Documentation and tools. If you dig into here, there's calculation guidance for torque, force, and torque. We say force, but torque, nonlinear, hysteresis, SEB, all that stuff's in there. The code's in there if you want to put it in Excel. Decision rule guidance. There's reliability studies. All this stuff is, like I said, it's just free. There's technical stuff.